Hello, I'm Matteo Marra and I'm a PhD student at the Vrije Universiteit Brussels. Today I'm going to present you my work on framework-aware debugging with stack tailoring, done in collaboration with my advisor, Elisa Gonzalez Boix, and Guillermo Polito from the Hermod lab at INRIA Lille. Here you can see the screenshot of a debugger opened on an exception happening while handling an HTTP request within an HTTP framework. So you can see the call stack depicted in this debugger shows on the top two stack frames related to user code in which the request handling generates a division by 0, and a number of framework frames under the dotted dash line that actually represent the execution of framework calls and represent the internals of the framework, in which the developer is normally not interested into since it doesn't have knowledge of what goes on there. This is a similar pattern when debugging unit test code, in which in fact framework code is wrapped within different user calls. And the actual methods that may be needed in the execution, such as the setup or the teardown method, are not represented in this call stack because they happen in another call sequence. Or when debugging promises, in which the developer sees a stack about the failing promise, but that does not include information about the creation of such promise. We can abstract these situations into three problems. The first one is that sometimes debuggers show too much information to the developer in the call stack, and developers have to distill framework code from user code and may even step into this framework code, hampering the debugging experience. Sometimes instead, debuggers show too few information, meaning that sometimes important framework-related frames are not present anymore in the call stack because they were either in another method activation or they were even executed in a different thread. Finally, sometimes debuggers show dispersed information, meaning that debugging information sometimes may be dispersed in different debuggers or stack traces, and debuggers do not show a unified view of such information, and developers need to go look themselves in different places for it. Before delving into the three problems, I wanted to give some background on what we consider as call stack. Since this talk is about online debuggers and about the call stack, we believe this is actually pretty important to clarify. For us, a call stack is a linked list of stack frames in which each of the stack frame holds a reference to the method it activated and holds a reference to all the arguments, temporary variables, and since we work in an object-oriented environment, a reference to the receiver of the method. It is a linked list, so each of the stack frames also holds a reference to the sender, so actually the stack frame that activated it. Now, going back to the problems, here you can see a typical example of a stack frame showing too much information. We abstracted it into a more generic call stack in which you can see on top the exception frame, which is normally called by user code because we are analyzing cases in which is actually the user code generating an exception. Under this, there is a frame that we call framework exit point, which is actually the stack frame that performs a callback to the user code. Under this, there is a set of different framework code, so of frames related to the internals of the framework, which eventually reach a framework entry point, so actually the frame that activated all the framework code. This is the one normally represented by an API call of the framework that is called by the user. So this is a typical example of too much information because the user most probably is not interested in the information depicted in the information given by the different framework. State of the art tackles this with the use of stack filtering. So the debuggers for common IDEs like Eclipse and IntelliJ offer some stack filtering abilities to filter stack frames based on known libraries or based on locality. so on, for example, their package. In this slide, instead, you can see an example of missing information. So we have a call stack of a unit test execution that is failing with an exception. On top, you see again the exception frame called by user frame, and then you see a set of framework code with entry and exit point, and again user frame in the bottom, which activates the whole stack. But these framework frames that are depicted in gray actually does not include the setup method, crucial in unit testing since it initializes the environment to be ready for a certain unit test. This method may be crucial for the developer to identify bad initialization of some instance variable that may cause the test to fail. Tools try to deal with this through framework-specific visualization. An example is the moldable debugger that tries to offer different visualization of the call stack depending on which framework is being debugged, but not necessarily can actually show this information and make it available to the user while debugging. In this slide, instead, you can see an example of dispersed information. For instance, we talk about a promise execution, so an asynchronous promise execution in which there are actually two threads, the one resolving the promise and the one creating. So starting from the promise creation thread, you can see from the bottom user code, which actually calls the promise API to create the promise. And then you can see the frames that actually schedule the computation that was promised in the developer's code, and that is actually executed on the other thread. On the other thread, you can see again framework code, which actually starts the execution of the actual promise, and then you can see user code, which is included in the promise runner, so it's the code that the developer promised, and the exception. When debugging, normally developers can see only the promise resolution thread and it's stuck, and the promise creation thread is either lost or not shown to the developer during debugging. State-of-the-art deals with this in different ways. So some approaches include the use of asynchronous stack traces to provide a stack trace, including both of the stacks, or some visualization to show the state and the propagation of the promise, or to provide online debugging of promises by linking the two stacks using proxies. Finally, another case of dispersed information is the debugging of a failing parallel execution in which more than an exception happens in two different locations, actually representing the same exception. If debuggers are available on this exception, there is either one debugger only on one exception or two debuggers each on their own exception. But debuggers do not abstract that this is actually the same exception, and this could be used at the benefit of the developer. So we have dispersed information into threads. To solve this problem, we propose Sarto, a library for framework-aware debugging with stack tailoring, providing a versatile approach that allows framework developers to delimitate framework code and to define which operations should be visible in the call stack depending on their own framework. And they can do so through using different stack operations that provide different functionality. We will go through them in a second. And we apply this approach to 4 use cases: an HTTP server, unit testing, debugging of promise code, and a big data parallel execution framework. Here you can see an overview of the 6 stack operations. So to deal with the problem of too much information, we propose to use stack cutting. To deal with the problem of missing information, we propose the crafting of a stack frame. And to deal with dispersed information, we propose 4 different operations. 1, to concatenate the call stacks, and 3, to actually compare, calculate, and apply difference between call stacks. To showcase the stack cutting operation, we use our example of an HTTP framework, so an exception happening while handling an HTTP request. As you can see in the call stack, we have on top an exception frame followed by user frames, so frames related to user code, directly followed by the framework exit point marked in orange. Under this framework exit point, you can see framework stack frames that are now depicted in gray because through the stack cutting operation, we cut those framework frames at the framework exit point. In fact, the framework exit point gives us a generic definition of which point the stack should be cut. You can see this reflected in the debugger that only represents the frames that the developer might be interested into when debugging, so the user frames and the framework exit point. We use the stack cutting operation also when debugging unit tests, but this time cutting between framework entry and exit point. At this point, though, we make use of the crafting a stack frame operation, which produces a new call stack by inserting a custom stack frame in between two other different stack frames. You can see this in action in the debugger, in which the setup for debugging frame is added between framework entry and framework exit point. And in this setup for debugging, we instructed Sarto to construct a method which puts the code of the original setup method and then does the explicit call to perform tests, inserting in the stack a method that was never there but that is still useful for debugging purposes. To debug promise code, we propose the operation of concatenating call stacks, which actually entails capturing the promise creation thread, and then based on the framework entry and exit point, generate a unique call stack. In this case, you can see that the framework entry point, so actually the API call that the user does to the framework, is in the promise creation thread, while the framework exit point is in the promise resolution thread. In the debugger, you can see the reflected call stack, in which the framework code in between is cut and a unique synchronous call stack is shown to actually debug an asynchronous execution. We show the last three stack operations in the use case of debugging parallel exceptions, starting by stack comparison. Stack comparison compares two exception stacks to determine if they represent two similar call stacks, hence two similar exceptions. Taken two stacks of two exceptions, A and B, stack comparison traverses them top-down in pairs to check if stack frames at the same position in the two stacks actually point to the same method and have the same PC. If this is valid for all of the stack frames, the two stacks, hence the two exceptions, are declared similar, and we can proceed to the delta stack calculation. The delta stack calculation produces a delta stack that contains only the differences between two similar stacks, meaning that a delta stack between stack A on the left and stack B on the right will contain the differences in variables that from stack A can lead us to stack B. In this case, analyzing a single stack frame, we can see that this points to three variables, divisor, dividend, and self, as does the one on the right because they're from two similar stacks. And we can see that while dividend and self point to the same value in the two frames, the divisor points to two different values, one on the left stack and two on the right stack. In this case, a delta stack is generated, and for this particular stack frame, it will have two placeholders for each of the variables that does not change between the two different stacks, and contains a 2 as the variable that differs, leading to the representation of the delta between stack A and stack B. Finally, we use delta stack application in a debugger to actually allow developers to debug these different exceptions. As you can see, the developer can choose in this view between the different data that cause the exception and actually go and debug the different call stacks. In fact, this is a display of almost all of the functionalities together, because when debugging a parallel exception, we cut the stack to hide framework code, we generate a stack frame to actually display some important information about the framework, and we use the 3 delta stacks operation to provide such debugging experience. To evaluate our approach, we provide our user experience in the 4 frameworks, and we also run a performance analysis to check if our approach introduces overhead in the exception handling. I will not go too deep into the performance analysis. It suffices to say that our benchmarks show that the Sarto does not introduce noticeable overhead into the execution, but I would like to spend 2 words over the experience in the 4 frameworks. So you can see on the left which operation has been applied to each framework, but I actually wanted to show you how a developer can, for example, add a framework exit point. So in this case, we are in the case of Zinc, which is the HTTP server in Faro. And you can see that the developer adds an annotation in the code, in the method handler request, which actually represents the exit point, saying that this is the exit point for the Zinc framework. And Sarto will then recognize this exit point when debugging and hide the framework code in the debugger. So that's it. Today I presented you Sarto, framework-aware debugging with stack tailoring, which provides a set of stack operations to tailor the call stack as a framework developer thinks it should be tailored for debugging. By following the QR code or the link in the bottom right, you can actually see a demo of Sarto in practice through the parallel exception, so the parallel execution frame. You cannot actually see how the framework developer can use Sarto, but you can see the final result, so how these operations actually display in our debugger. And on the left you can find my contact information. Thank you very much for the attention.